We are going to talk about logical equivalence. We began our propositional logic study, how to express statements, and now again it's similar thing. You can think of it in terms of linguistic. It's a translation of statement, rephrasing a statement in other words for various reasons. Okay, this is a quick summary of what we did so far. We talked about proposition. That's a statement of a description of something, a statement, and a statement which is either true or false, not both, not neither, is called a proposition. Then we built further proposition from atomic existing proposition. We talked about negation of a proposition, then combining two proposition into a compound proposition using and, or, not, if, then, and exclusive or, and if and only if in those things. We said that if we are given a compound proposition, we can find its truth value, truth table, its possible values for all possible inputs, right? Its output for all possible inputs, and we also could make, given a truth table, we could make up compound propositions from them, right? So today we talk about when two propositions are equal and how we can translate a proposition, compound proposition, into other propositions. Okay. So for that, the first term that you should know is a proposition, a compound proposition is called a tautology if it is always true. Okay. It's a compound proposition made up of two or more atomic propositions. So if a proposition remains true for all possible values, truth values of its atomic proposition, it's called a tautology. Okay. So we'll give you examples of these things. Another proposition, a compound proposition, is called a contradiction if it is always false, right? For all possible values of the input of the values, truth values of the atomic proposition, the compound proposition is always false, then it's called a contradiction. It's called a contingency. Otherwise, if it's not a tautology nor a contradiction, if it's not always true and not always false, then it's called a contingency, meaning it's for some combination of values, input values, the output is true, for others the output is false. Okay. So here is an example of a tautology. It's a compound proposition P or not P. Okay. So there are two atomic propositions, one is P and the other is the negation of P. So the possible values of the atomic propositions are P is true and not P is false, and P is false and not P is true. Okay. So these are the possible values. For this value, what is T? If I take a disjunction or of T with F, what do I get? T or F. If one of them is true, the output should be true, right? So P or not P is true when P is true and not P is false. And similarly, P or not P should be true when P is false and not P is true. Okay. This makes sense? You see in the last column, the truth values, all possible truth values of the compound proposition is true in all rows. That's why we call it a tautology.
The definition was it is for all possible truth values. So yeah, TT and FF.
Good. That's a very good question. So the question is, we define tautology to be something that is true for all possible values of the atomic propositions. Okay. Here there are two atomic propositions. Actually, if you think about it, there is only one atomic proposition. That's why there are only two possible values. Because when P is true, not P cannot be true. So that's not a possible valid legal input. Is this clear now? It's not actually two proposition. TT is not a possible input to this compound proposition. Okay, it's not a valid combination. Similarly, false, false, because when P is false, not P cannot be false. Yes, please.
This is only applicable for mutually exclusive conditions.
So the question is this only applicable for mutually exclusive? Okay, so generally speaking, I don't like the words words that could cause confusion. We don't know what is mutually exclusive, or else we just said. So because there is mutual exclusion has a meaning, right? When we do set theory and then when you counting, this is a very important concept in counting and also in set theory. So right now let's not confuse it. There is nothing called mutually exclusive. P and not P are the opposite of each other in terms of their truth value. Okay? They are the negation of each other. So, when P is true, not P cannot be true. That is why I did not write T T as a possible input value, the possible values of the atomic propositions. Okay? So, here is another contradiction. Here your question would remain valid for this one compound proposition also, P and not P. What are the possible values of P and not P? What are the possible values of P and not P? Why is F not a possible value of P and not P? Why is F not a possible value? Why F rho does not appear when P is false and not P is false? Yes, please. Yeah, so because they are the negation of each other, if P is false, not P cannot be false. Okay? And similarly, if P is true, not P cannot be true. So, this is not a possible value combination of the atomic propositions. Okay? Strictly speaking, again, there is only one atomic proposition, right, and there are two possible values of the atomic proposition. Now, not P is derived from P, it depends on P, it is not an independent atomic proposition. Okay? It itself actually is a compound proposition or a derived proposition from another atomic proposition. Yes, please. No. So, I will give you many more examples. We do not always do the contingencies, contradiction and tautologies are not always made up of just one proposition or just the negation of a proposition with this negation. Okay? I am going to give you more examples here very soon. Let us see why should we study it, and we are going to study it for a purpose of establishing equivalence. Pretty soon we will get rid of it, we will not mention it too much later. But right now you hopefully will relate more to this thing. Can you, I am asking a question, all of you have some programming background, right. So, here is a code, a piece of code, while I is less than or equal to 10, or that is the logical or. In C++ you will write a double pipe, in other languages there will be something, C++, Java, C will be a double pipe symbol. So, if I is less than or equal to 10 or 5 times I is less than or equal to 50, then execute this code, increment I by 1, right. The question is how many times this loop iterates, how many times will I be incremented? Yes, please. How many times will this statement executed? Infinite times. So, his answer was this is essentially P or not P. That is why it will be running, it will run for a infinite many iteration. Somebody else wanted to say something? Is this clear to everyone? So, yes, please. That is very good thing. We will come to that. These are actually more than one proposition. I is less than or equal to 10. Good. So, we will going to come to that. We will make a compound proposition that are tautology made up of 3 or 4 different propositions, and you can do it as many propositions as you want. Yes. That depends. So, will the tautology condition always result in an infinite loop? A very good programming question. So, yes, please. Okay, that is good. So, his answer is yes, unless we somehow block it some other way. Yes. You do not get why this is going to infinite loop? That is very good question. Because that is not really our thing. Look at this, what does this statement say? If the I is an integer, is a variable, it has certain value, right, big or small or something. That value is either smaller than less than or equal to 10 or it is greater than 10, right. This is called the trichotomous law or the dichotomous law. A number is either less than or equal to 10 or bigger than or equal to 10 or bigger than 10, right. It is either less than or equal to 11 or greater than 11. That is for any number, this is true, right. For any I, this is true. So, now this statement is I is less than or equal to 10. This statement actually is I is greater than 10, right. If you cancel out the 5, this is I greater than 10. So, In programming, this is how we make mistakes, because this is not really obvious, and that is why a compiler which has no intelligence, or it will not perhaps catch, many compilers or preliminary compilers will not catch this type of error. It will not give you those errors that this possibly goes into infinite loop, right. Maybe some will do. So, now this is just, this statement is either this is true if I is 1 or 2 or negative 17 or 0 or 9 or 10, the first proposition is true, or if I is 11 or 12 or 19 or 9900 or whatever, then in that sense the second proposition will be true. Exactly one of them will be true, right, at least one of them will be true. If we wrote here 5 I is greater than or equal to 10, greater than or equal to 5, 50, then at least one of them will be true. If I is equal to 10, then both will be true. Nonetheless, this condition will evaluate to true for all possible values of I. So, this loop will run infinitely, there will be infinitely many iterations there, right. So, that is where a tautology, you should be, as a programmer, you should be interested in knowing what is a tautology and when is why should you be worried about it if it appears in a program in an unintended place. Okay. Here is another example. If some variable num is greater than I, assume both num and I both are integer, then there is a nested body within the body of this if number is equal to I, num is equal to I, then print the statement I was here. So, how many times will this statement be printed? How many times will this statement be printed? 0 time. This statement will not be executed. Okay, I was here will never be printed. Why is that?
So, assuming that initially your number was greater than I, our program will enter the if block.
Yeah.
Then it's not possible that if the number was greater than I, it be equal to I. So, it will never be equal to
Okay. So, the answer is num is a variable, it is an integer variable, it is either bigger than I or smaller than the value of I, right, or less than equal to or greater than I. If it is less than or equal to I, it will never even enter the outer loop, the outer condition will fail, it will not go to the inner controls ifs, right. But if it is bigger than I, strictly bigger than I, then it will enter the outer control, the outer if condition is satisfied. So, it will start to execute the body of the inner condition, but then the inner condition says if the value of num is equal to I, it was already bigger than I. So, now it cannot be equal to I. So, this condition will fail, okay. This will fail, and this is this statement will never be executed. I just want to point out a subtle point here, that these two conditions are not the negation of each other. Is that true? These two conditions, num greater than I, num equal to I, are not the negation of each other. So, here is a contradiction not made up of the and of two negated proposition, two propositions that are negation of each other, right. Num greater than I, its negation is num less than or equal to I, not num equal to I. Okay. So, because it's both, if num is less than I, if num is less than I, suppose I is 10 and num is 7, then both of them are simultaneously false. That is why they are not negation of each other. Okay. So, anyway, this is this statement will not be executed because the condition makes a contradiction. It is always false, right. The compound condition always false. So, now here is a proposition, a compound proposition made up of two distinct propositions, and the question is if it is tautology. Keep sitting please, he will bring it to you. So, P and not P and P or Q, the whole thing implies Q. Is this a tautology, right? So, how do we actually know the truth value of a compound proposition? We saw this earlier. How do we find the truth value of a compound proposition?
Sir, we can break this down into different propositions and then solve them individually to get their truth values. And then
Okay. So, break down this thing, those breaking down is part of a process. Yes, please. Yeah, make the truth table of this compound proposition, the only way we know how to establish all possible values, truth values of a proposition is to see its truth table. Truth table, the definition is all possible truth values of a proposition. Yes, you wanted to say something?
Saying that you only have to find one value where it's false.
In this particular case, yes, because we want to establish whether it's a tautology or not. So, if it's not a tautology, we may have to just find one possible combination of P and Q for which this thing leads to false, that will establish it's not a tautology. But my sub question was how to find the truth value of a compound proposition, right? We make their truth table. Okay. How do we make truth table of a compound proposition? We begin with the smallest atomic propositions and we gradually compound them using the rules we saw last lecture, and then we will give it the truth table of increasingly bigger compound proposition until we get the whole proposition. Okay. So, in this particular case, we begin with the truth table of P and Q, that is 4 possible values: true, 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 false, false, true, and false, false. Right? We get these 4 possible values. Then what is, if P is true, what is not P? It's not P is false, and if P is true, not P is false, then for false, false we get true, true. Then we take the compound the truth values of P over Q for each possible values of P, Q. We know how to get it, the P over Q. It will be for the true, 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 false, true, false, true, true, and false, false is true. Right. So, this is the truth value or the truth table of P over Q. Then we make the truth table of the previous column, and the column before that we take their AND, we get the truth value of this whole proposition. Then we find this column implies this column, the Q column, and we get the truth values. Okay. What do you see in the last column, the red one? What do you see in the red column? It is all true. So, now pronounce it to yourself. For all possible values of P and Q, because this compound proposition is fully determined by P and Q, right. Once we know the value of P and Q, we know the value of this compound proposition. So, for all possible values of P and Q, we get that this compound proposition is true. That is the definition of a tautology. So, this proposition is a tautology. The last column of this proposition, look at this proposition. This is this whole thing, this in brackets, in parentheses, this is called the hypothesis. This Q is called the consequence, or the condition, and the, what is it called? The consequence and the conclusion. Yes, the conclusion of this. So, the premise or the hypothesis, we will take the truth table or the column of this, the hypothesis, which is this column, the second to last column, and the conclusion column is Q. So, we will take their if then thing, right. So, if the premise is true and the conclusion is true, what is the value of the proposition? What is if true then true? The implication is true, right. What is if false then false? This is a true statement. If false then false is true, right. What is if true then true? That is also true. If true then true, and if false then false is also true. Is it clear? If 1 is equal to 2, then I am the Pope is a true statement, right. Yes. Please say it again. If false then true is a true statement. Oh, that is a good thing. So, that is what we spent a lot of time on this. Let me quickly repeat this. An implication statement, if A then B, is only false when A is true and B is false. If the condition is true, the condition is met, still the conclusion does not hold, the conclusion is not true. So, I gave you the example that if you solve the Goldbach conjecture, you will get an A, you will get an A in the course. The only way this statement will be false if you did solve the Goldbach conjecture and you did not get an A, right. If you did not solve the Goldbach conjecture and you still got an A, This is nothing to do with the statement. The policy is not violated, right? You may get an A because you solved some other big conjecture or some other reason. Is this clear? Did I answer your question? Somebody asked. Yes? Yes, please. The question seems to be a yes no question, so I think you should write yes no, or you could write the whole truth table. That's your choice. Is it a yes no question, right? True false question? Yeah. So you could just write yes. Okay. So that's why that you didn't need to write or talk too much. You can just stay with me, and then we'll do this. Okay. This purpose is just to make you stay in the class. Okay. So next one. Yes. Please.
एक लाइन की reasoning if you can add, please do that. Just yes no के बजाय don't make the truth table, just make it अपने पास. But it's like one of the lines that says to explain why it is that. तो बस वो एक reasoning that would help you in LQs as well.
Yeah. Okay. So the suggestion by Humaira is that if you can give some reasoning to the answer for your answer, it will be good. And the reasoning for this case, for example, would be that, well, look, the truth table for all possible value, the truth in the column for this proposition is always true. That's a good enough reason. Okay. Okay, we will streamline this. This thing will be established properly. Okay. So the next one is P, not P, and P or Q, whole and not Q, a contradiction. What is a contradiction? Can somebody tell me what is a contradiction? Sorry?
All possible truth values are false.
So, yeah, so for a proposition is called a contradiction if it is false for all possible truth values of the atomic proposition. How many atomic propositions are here? P and Q, two distinct propositions. So, there will be 4 possible values of the truth values of the atomic proposition. Okay. So, we will again do the truth table, gradually build it up for increasingly compounding propositions and find their truth values for these So, we first get not P, then P or Q, then not P and P or Q. That will be just the end of these 2 columns, and with the not Q column, and we get that it's always false. This compound proposition is false for all possible truth values of P and Q. So, you can write again with this short reason your answer, whether it is true or false, and it happens to be true. Yes, thank you. Okay. So, for our reason, so it is one thing to know about what is a contradiction and what is a contingency, what is a tautology. This is our real purpose of why we are studying it, right? Makes our life very easy. This is a very practical thing, establishing logical equivalence. Okay. So, two compound proposition are logically equivalent or just equivalent. We write it as R. If R is one compound proposition and S is another compound proposition, we write it as R with this double arrow, left right arrow S, right. So, R is equivalent to S is a tautology. If and only if S is a tautology, then we say R and S are equivalent, logically equivalent, right. Logically, they are exactly the same proposition, they are a translation of each other. It is a rephrasing of the same proposition in different words. Is this clear? See the word tautology here? That is why we were studying tautology. So, we write it like this: R is equivalent to S, or R is equivalent to S. Another notation is this left right arrow, the slash capital L capital R arrow slash left right arrow, or R is equivalent to S. That is how it is pronounced. Remember this truth table? This is a truth table of if and only if. P if and only if Q. When is it true? When both have the same truth value. And when is it false? When P and Q have opposite values or different values. Okay? Because opposite and different is the same thing, we are talking about binary, right? Yes, no, true, false. So, if when P and Q are similar values, both true or both false, if and only if. That is why we say that a proposition R is equivalent to another proposition S if their if and only if is always true. So, just think about it. R if and only if S is always true. What does it mean? Can you pronounce it in terms of these truth values of if and only if? What does it mean R if and only if S is always true?
When R is true, S is true, and
Yeah. So, yes, when R is true, S is true. Yes, please.
Both have the same truth value.
So you didn't say the word always. R if and only if S is always true is a tautology, meaning is always true. So where is this always coming from? R if and only if S is a tautology means, yeah. So these R and S are always equal, right? And that's what we say equivalent. They are equivalent when one is true, the other is true. When one is false, the other is false too. Okay, that's why we use it. So we know that P if and only if Q is true whenever P implies P is equal to Q. That's why we say that two logical equivalent are equivalent. Two propositions are equivalent if the if and only if between them is a tautology. Okay, so they have the same truth value. Then this follows from the biconditional statement. Yes, please. Yes, there is no tautology. There is no R and S here. This is not talking about R and S. This was just a recollection of our definition of if and only if Q. Okay, so let's see. When I say R if and only if Q is a tautology, can you put it different words, rephrase this statement? R if and only if S is a tautology. So another way to say R if and only if S is a tautology is R if and only if S is always true, right? Further rephrasing, R if and only if S is always true is equivalently to say that R and S always have equal values, right? And that's why we use if and only if, the tautology of if and only if between two propositions to say that these two propositions are equivalent. Yes. Sorry, please. R and S, we need to know what is R and what is S. Generally, they will be compound propositions, right? So that's why I can't make. So R and S ka truth table, we really can't do this because we need what is R and what is S, right? If it is made up of three further proposition or four further proposition, but I'm going to give you examples of this. Yes.
So for example, if there are two different logical statements, तो लेकिन उनका ये same आते हैं, तो इसका मतलब वो दोनों same है.
Yes, they are the same. This is a rephrasing of the same statement, just saying the same statement again, right, in different words. I'm going to give you examples, and so first let's see why would we need something like this. It's very important to restate something, simplify something. I give you an expression, then I restate it perhaps in a simpler word, but my restatement cannot be different, right? If I make it different, then it's not restatement, it's a different statement, right? So it has to be equivalent. But why did I use another form? Because maybe the other form was simpler, right? So here is a computer program, it is if condition, a very elaborate if condition. Maybe you can simplify it. Instead of writing 3 lines of code, maybe you can condense it into 2 lines of code. It will help in testing, it will help in identifying errors, it will make the programming easy, it will save you time perhaps, right? Most probably, most importantly, it's used for, it's called circuit minimization, right? You have one circuit. We told you yesterday that there is a circuit, these are and or, and these are all just digital circuits foundations, right? So you get one compound proposition, meaning one circuit. Now you rephrase this proposition, meaning you redesign the circuit with equivalent functionality, with exactly the same functionality. Whatever you input, the output will be exactly the same for both the circuit. But the second circuit may be much cheaper to make. Maybe in your lab, in your toolbox, you just don't have AND boxes, AND gates available. So you rephrase it, you write it differently, so it doesn't use as many AND gates as you would like to. And now you have a cheaper version of OR gates and cheaper NOT gates available. Use that. Okay. So circuit minimization or circuit translation, that's one thing. Another thing which is used a lot by in language processing and other stuff, but also for computer program. You give me 2 programs. What's important in a program? Not the assignment statements, not the arithmetic statements. The important thing in a program is the flow. The flow is determined by the conditions of the iteration, the loops, and the conditions in the conditional structures, right, the ifs and switches and those things. I can check if two computer programs are equivalent by just checking if the conditions, the compound proposition representing program 1 is equivalent to the compound proposition representing program 2, right. We will see those examples also in a minute. So, look at these two circuits. Both of these circuits are exactly the same, have exactly the same output. Okay. They have input, the first one has input x, y and z, the second one has input x and z only. This is just one AND gate, this is the symbol we use for AND gate. This will be true or high voltage if both of these have high voltage. If any of them is lower voltage, low voltage 0 volt or both of them, then this will be output will be false, right. This circuit and the above circuits are exactly equivalent for all possible values of x, y and z. The second one does not even depend on y, right. The first one has a useless input y, which doesn't make any difference to the output, right. But how many circuits are, how many components are used in the first circuit? This is the one AND gate, another AND gate, and this is a OR gate, and here is a NOT gate, right. This AND gate is very expensive gate, it is not actually an AND of 3. So, it is actually 2 AND gates. Okay. So, this one is using 1, 2, 3, 4, 5 gates, and this one is using only 1 gates, right. That is what is called circuit minimization, right. So, I use the picture from sketsoft.com, the examples 2 circuits with exactly the same output for all possible values of x, y and z. Yes. Yeah. So, sorry, say it again, please. Yes, both. Yeah. So, that variable does not make any difference in the output.
So we are considering the pulses output. What is the output?
No, so true, false. So, you don't know logic circuits. You know, are you guys taking CS 225? The digital system fundamentals, computer system fundamentals. Yes. So, those of you who are taking those things, the computer science major, it should be not an issue, but this is just, we defined it as AND, in the verbally we talked about it, and that is what it is. This is how the symbol for that. In circuits it will give output when both the inputs are 1 or true. Okay. So, look at this thing, this perhaps you would like, you will appreciate more or relate to. Merging is a very important, very important step in many different problems. Merge sort is one example based on merging, finding ranks is another, and other stuff is just a very important operation. Merging is, if I give you two sorted arrays, two arrays that are sorted in increasing order or decreasing order, assumed increasing, you want to merge them, but you do not want to disturb its sortedness. So, the output array, the union of the two things, even though we do not know union yet, but we combine all the numbers in A and B, but we want to output in the sorted order. Okay. So, here is an example, here is an array of 1, 2, 3, 4, 5 sorted, here is another array of 2, 3, 7, 8, 10, 2 and 3 are repeated, both arrays are sorted, you want to combine them. So, it will be 1 and then 2 2s and 2 3s and then 4, 5, 7, 8, 10. Is this clear? This is called merging. Here are two pieces of code that are achieving, both are achieving exactly how you would use when you do your data structures in algorithm, you learn merge sort. This is a step in merge sort, is called merging. Both of these code, you see they are checking the values of I and j, the indices, what is the current element of A being processed, j is the index of what is the current element of B being processed, and then their values, right. AI is less than or equal to Bj, then k is the current index, the first empty index of C. See this one code, here is another code. That is what I told you, we can check if these two programs are equivalent, if both these programs are actually achieving merging. Okay. Seemingly very different, there are ANDs and then there are ORs. Here there are different ANDs and ORs, maybe different gates, right, many different ANDs there and many different ORs there, and a lot of less than or equal to this. Does this make sense? Equivalence of two logical propositions, two compound propositions. Okay. Do not worry too much about it, we're going to learn how to prove two things being equal. I just wanted to let you know that there are a lot of applications of these things. Okay, many different applications. We will actually study many more, and when we do set theory and other stuff. Okay, so the source of this thing is, so it should be there in the, if you zoom into the PDF, because it's a vector graphics thing, you will see the thing. I forgot where did I get the image from. So we know what is a tautology, we know what is a contradiction, and what is a contingency. We know why do we need them, right? Especially in computer programming, because we know that's our first thing. We defined the equivalence of two logic compound proposition. Two compound propositions are equal if the if and only if between them is a tautology. That's how we define them, and then we saw some seemingly different but logically equivalent compound propositions. Okay, yes please. What was? Oh, contingency is a logical proposition, a proposition which is neither tautology nor a contradiction. So, a general meaningful thing. Something that is always true is not really meaningful, right? Something that is always false is not really meaningful, right? If a circuit always gives the output high voltage, or its light is always, there is just no pieces of information. If a circuit is always just off, it does not make much sense, right? You can't really put it to use, any meaningful use. So, a contingency is a proposition that is neither true always nor always false, right. So, sometimes it is true for some input combination, for other input combination it is false. Okay. So, now we are going to talk more about logical equivalence and how to prove it, right. So, we saw one way to do it, just proving logical equivalence using truth table, by taking the if and only if between them and establishing whether it is a tautology or not. We will now determine other ways to do this. This is a quick review of what we defined: two things to be equal, two compound propositions are equal if the if and only if between them is a tautology, right, and we saw an example of this. So, to check whether it's two propositions are equivalent, we make the truth table of R depending on what is it built upon, what are its atomic propositions, and we make a truth table of S depending on what are its compound propositions. We take their if and only if between them. If it is a tautology, the last column is all true, then we say they are equivalent, right. So, here is an example: is the negation of P and Q logically equivalent to the negation of P or the negation of Q? If not P and Q, equal to not P or not Q. Please do not write and do not jump to answer, talk to me first. Can you, is the question clear? Can you rephrase the question, or how would you go about it, red shirt? How would you go about this? You are going to write something. So, now question लिख रहे थे, question का लिखना का ज़रूरत नहीं है, just write question number, okay, the problem number. Anyone, how would you go about it? Truth table बना के क्या करोगे? Yes, somebody wanted to say something. Yes, please.
We'll see if they are if and only if the relation that proof value of x equals possible.
Okay.
Take the if and only if.
Okay. So, the suggestion is that we take the if and only if between what is written on the left side, the negation not P and Q, and not P or not Q. We take their if and only if between them. We know how to take if and only if between two propositions and see if that is a tautology. Okay. So, how would you make the truth table of not P and Q? How would you make the truth table of not P and Q? Please, what should be our next column? Somebody. Can you guys not write and just talk to me, please, for now? What should be our first column? Yes, next. Not P, okay. Yeah, so there is no order there. So, but it should be not P should be there somewhere, not Q column should be there, and P and Q should be there, and not P and Q should be there, and not P or not Q should be there, and then there should be a tautology. So, first one, because I forgot what order did I draw it, so that is why I did not want to actually ask a question. So, not P, can you tell me please the column not P, someone here? False, false, true, true. Can you tell me the truth table, the column for not Q? False, true, false, true. Now, the next one should be the OR of these two, not P or not Q. Which two columns should be OR? The third and the fourth, right? The third, the not P column and the not Q column. What is the value? What are the values there? Tell me the values of not P or not Q. Just say something, anyone. False, true, true and true. Yes, so it's false, true, true and true. Then we will take the AND of these two. Tell what is the AND of P and Q? True, false, 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 right? And then we take the negation of that, which is false, true, true, true. Now, if I take the if and only if between this column, the two red columns, what will be the, shall dictate to me what will be the if and only if between the two red columns? False, if and only if false is true, true if and only if true is true, and then true if and only if true, and then true if and. So, the negation of these two columns, that the if and only if between these two columns will be a tautology, right. We can observe that it is going to be a tautology by just observing that these two are actually equivalent. For all rows, they are equal, right. F and F true and true, F and F true, 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 whatever. They are both, if one is true, the other is true. One is true if and only if the other is true, and one is false if and only if the other is false. Yes, please.
So in this case, that means we can only check that equivalence if they both rely on the same method.
Yes, that's a very good question. So, the question is, or that's the comment is, because the left hand side is also made up of P and Q, and the right hand side is also made up of P and Q, that is why we can establish whether they are equivalent or not, right. It is a correct observation. If the right hand side was using some other proposition, atomic proposition R, right, and the left hand side was using some other proposition S. So, then we can, it does not even make sense to say whether they are equivalent, right. Remember the equivalence thing. The if and only if is a tautology. Tautology means for all possible input combination, they are always true, right, or always equivalent in this case. Now, it is not all possible input combination does not even apply to both of them. Okay. Maybe it is not the fully correct, technically correct answer, but this should satisfy us for now. We can talk about it later off the class, or next time you can ask me. I will just find out how what's the right phrasing of that thing. Yes, please.
If we are able to do this tautology pathological equivalence, ऐसा क्या केस होता है कि we accidentally get it through coincidence and not causality, कि we cannot be sure it's actually supposed to be the same coincidence?
Okay, so the question is, what if, so if I understand the question says, can we do some kind of causal analysis? Why are these a tautology? Why are they equivalent?
Like, is that like, is it understood then that there's a causal relationship? Yeah, possible है कि coincidentally भी हो जाए ऐसे?
There is causal relation. I do not understand what is causal relation or what is the causal analysis here. This is equivalence. This is very possible. It is understandable that I can say, I can state the same fact in many different words, right. I can get the same answer using many different computation. I can achieve the same output using many different circuits, physically different, but the output functionally they are the same. Structurally different, functionally the same. That is a very possible thing, right. That is very understandable. And if I ask you to write two people or 10 of you to solve a given problem, you may write many different codes, but functionally equivalent, right, in terms of correctness and incorrectness and output for all possible values. You can meet the requirement specs many different ways. Yes, please.
Sir, is it possible that the values of the individual compound propositions are equivalent, but they don't have tautology?
That's a very good question. Is it possible if two columns, if I put these words, if both these two columns are exactly identical, yet if I take their tautology, their if and only if, it is not a tautology? That's your question?
Yes.
No, that's not possible. That's a definition of if and only if. If and only if says if you take both trues, you will get a true. If and only if both false, you will get true. If and only if true and false, different thing, then your output will be false, right? So it's not possible. It's just rephrasing the same thing. Okay. Yes, please. We can't really compare them. That was the question earlier too. We can't really compare them because no, it depends. So, like in the previously I saw with the diagram that we used, there was this extra variable y, but that y was just introduced just to make this point. The y was not doing anything, right? Y was just being ORed with. This will come in a minute when we do some logical thing. There are some obvious tautology, some obvious contradictions. So, they are just useful. Any constant input is basically useless. It does not make anything. Okay, just give me, hopefully in about 5 slides you will answer. You will be you will get your answers. Okay, if not, we will talk about it. Okay, so the corresponding columns are equal, right? So, if you take their if and only if, you will get a tautology. So, now your answers to this question should be yes, this is true because the corresponding columns are equal. If I look at the truth table, for all possible values of p and q, both the left hand side and the right hand side gives the same value, right? They output the same thing. So, they are equivalent. Here is a next one, p implies q is equivalent to not q implies not p. Did you see this before? P implies q is the same as not q implies not p. What is this thing called? No, when I say these are equivalent, do we have any other words of it? We saw it earlier. Let her say. Sorry? They are equivalent. Yes, that's true, but do you know, can you rephrase this statement? Someone else, please. Yeah, any implication is always equal to its contrapositive, right? You can restate an implication by its contrapositive, using its contrapositive, and they are equivalent. They are just the same statement. Is clear? We saw this last time. We spent a lot of time on this thing, that the contrapositive is just another way of saying this thing. An implication is not equal to, we saw yesterday examples and we convinced ourselves that implication is not equivalent to its inverse, it is not equivalent to its converse, it is equivalent to its contrapositive. Okay? So, how would you prove this? You make the truth table of p implies q and also the truth table of not q implies not p, it is contrapositive. You take the if and only if between these two columns, these two compound proposition, and you observe that the if and only if is a tautology. Okay, so that's the way we defined equivalence between two propositions. These two compound propositions are exactly the same; they are equal. Okay, now if you say, if you solve the Goldbach conjecture, then you will get an A. This is equivalent to saying you did not get an. If you did not get an A, then you did not solve the Goldbach conjecture. These two are exactly the same statements, right? Does not say anything about whether you solved the Goldbach conjecture or whether you got an A or anything. That is a separate compound proposition values, but for all possible, the compound propositions are basically rephrasing of each other. Okay, here is if p implies q is equivalent to not p or q. Look at this statement. Yesterday I made a statement in last session that this p implies q, the if then circuit, the if then thing is a derived circuit. Our fundamental compounding operations are not negation, disjunction or and conjunction and. These three are the fundamental thing. Everything else is derived from them, right. This one says, you see what P implies Q is actually made up of not P or Q, right. It is made up of not P or Q. Just take not P or Q and it will be equal to these two are just equivalent statement. Make sense? How would you prove this? Make the truth table of P implies Q. We know how to make the truth table of P implies Q. It is only false when P is true, the condition is true and the conclusion is not true, Q is false, right. Otherwise, it is true. Then you take the truth table of not P or Q. We know how to make not P, we know how to take it or with Q. You get that its truth table is true, false, true, true. If you take the if and only if between this column and this column, what do you get? What is true if and only if true? And what is false if and only if false? They are both the same, output will be true. True if and only if true, both the same, output will be true, and again true if and only if true, output will be true. They are the same. So, the output, the if and only if between the two compound proposition is a tautology, hence these two are equivalent. Okay. Now, in English, for those examples that we did last time, if I go for a walk, then it will not be raining or whatever we did the example. If you solve the Goldbach conjecture, you will get an A. Look at this. Okay, so let us say P is you solve the Goldbach conjecture, Q is you get an A in the course, right. P implies Q is if you solve the Goldbach conjecture, then you get an A in the course. Can you say the same thing in terms of P and Q? This not P or Q? Can you say what is not P? You did not solve the Goldbach conjecture, or you haven't solved the Goldbach conjecture. And what is Q? You got an A. So, if I say if you solve the Goldbach conjecture, you will get an A, is equivalent to saying you either did not solve the Goldbach conjecture or you got an A. Think about it in English, in any language in natural language you put it, these are exactly the same statement, right, and that is what this logical equivalence is telling us. Here is a more a little bit complicated compound proposition made up of 3 atomic proposition P, Q and R, and they are also equivalent by just making the truth table of P implies R or Q implies R. This is equivalent to P and Q implies R. Yes, please. Sorry. So, these two are also equivalent by just making the truth table and observe that the truth tables are exactly equal, right. So, now we have 3 atomic propositions and we made up the truth table is very long, right. How many rows will be there in this truth table? 8. Here is another one made up of, by the way, this is what we call, this is called the implication law. This is what we call the implication being equivalent to contrapositive. This is called the De Morgan's law. We are going to talk about it in a minute, and this one is called the distributive law of addition, of multiplication over addition, of AND over OR. Yes, please. It is not true, they are not equal. So, other than the second row, all are true. Another one, this is what we call the distributive law of AND over OR. Okay. Please help me here. What shall I do next? Q or R. You know how to take OR of Q or R? Q or R, what will be the value of Q or R for this in this row? When Q is true and R is true, what is the value of Q or R? True. And the rest of the values, right. For possible values of Q and R, we can make Q or R. Then we should make AND with the first column. What if we take the AND of the first column and this column, the Q or R column? Can you please tell me, somebody tell me the column? True, 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 false, then all false, right. First 3 are trues, the rest are all false. Then we should do P and Q. hopefully. Yes, P and Q, you know how to do it. Then we will do P or and R. There is a parenthesis, opening parenthesis extra here. We will get, can you please note a little bit there? Then we take the OR of these two and observe that these two are just equal, right? They are exactly the same. For all possible values of P, Q and R, all 8 possible values, the output value is exactly the same. And if you were to take the by implication between them, you will get exactly the same thing. Okay. So, this is a summary. We talked about the equivalence of two propositions. We talked about how to use truth table to verify if they are equivalent, or if their by implication is a tautology, or if the two columns just amount to be equal. Okay. Okay. So, we have a question also about which is going to come now, becoming very important. How many rows would be there in truth table? Sometimes it is too many, sometimes too few. This is actually a counting question. How many question is a combinatorics question, right? We have a whole section on this thing, but we cannot go beyond this point unless we have some basic idea. If you have one proposition P, how many possible values are there for P? 2. One is true, the other is false, right? A proposition is a statement which is either true or false. So, it is 2 possible values. Okay. If you have 2 propositions, how many possible combinations of value? Again, the combination is a proper word with a meaning, but the English word combinations. How many combinations of possible values are there for P and Q? 2 propositions. 4. Why 4? Somebody, can you elaborate on why there would be 4 values? Okay, I am going very slow and ready. So, how many? There are 4 possible values, namely true, true, both are true, both are false, P is true, Q is false, and P is false, Q is true. Okay? 4 possible values. So, if there are 3 propositions, then there would be 8 possibilities, right? Okay. So, we know how to establish the equivalence of 2 propositions, right? 2 compound proposition. This is equivalence using the truth table method. We make the truth table and observe it, indeed they have the same output values for all possible inputs, right. I am sorry, I am using the input output terminology is more either a computer programming or a circuit terminology, but for all possible values of the atomic proposition, the value, the truth value of the compound proposition is going to be what is the value? That is what we call the truth value of the compound proposition. Okay. So, we started with restarted the discussion with the length of the truth table, the number of rows in the truth table. So, if we have one proposition P, how many possible values are there for one proposition P? 2. Which 2 values are possible? True and false. If we have 2 propositions P and Q, how many different possible combinations of input values are there? If we have 2 propositions P and Q, how many different combinations of values of P and Q are there? Which 4? And true, false, true, false? True, false, true, false is not a different combination. True, false is. So, there are 4 possible combinations of values of P and Q. Both P and Q are false, false, false. Both are true, true, true. P is false, Q is true, or P is true, Q is false. These are 4 possible values, right. So, she asked the question, that is why I am going to repeat. And if we have 3 propositions, how many different values are there, different combinations of truth values of P, Q and R? 8. Which 8? Give me one of them. All 3 false, all 3 true, P, Q true and false, and those things, right. So, there are, that is 8 possibilities. Again, this is a combinatorics question. We will study it more systematically and much more complex thing, right. So, we were proving equivalence of logical propositions using truth table. This is a problem. This question, the reason I spent some time on question, because actually question brings the complexity of this methodology, that if you are going to draw the truth table of one left hand side of the proposition of the equivalence and the claimed equivalence, and write the truth table of the right hand side of the claimed equivalence. If they are equal, then you say the equivalence claim is correct, otherwise the equivalence claim is not correct. If those compound propositions are made up of 19 different atomic propositions, how many rows will you have to draw? 2 raised to the power 19, right? That's a big number. If there were 30 different propositions, how many different things will you have to make? A billion, right? Or in binary sense, a billion, right? It's too much, too many. And this is not it's not a hypothetical scenario when you will have to establish circuits to be equal based on 32 bits or 32 things. 32 is very small now. Any word size, any computer, your RAM, your register size and the data bus and the address bus of your computer, the word size, so called word size of your computer is at least 64 bits, right? So, the circuit working on these 64 bits is 2 raised to the power 64. 2 raised to the power 64 is a really big number, right? Nobody can actually draw that. 2 raised to the power 64 is really huge, right? I don't even know what's the right English word for it in terms of a zillion number of rows. Nobody can draw it. And it's very logical. 64-bit machine, 128-bit machines are quite common. Okay, in cryptography we will see later, we work with these type of numbers, 1000 bits number and 1024 bits number. It's like they are considered toys. Okay, there. So, if you have more atomic propositions, the truth table is going to be very large, right? Now, this is the question I asked already. If you have n atomic propositions, the number of possible combinations of values for all of these truth table is going to be 2 raised to the power n, right. So, for 5 it will be 2 to the 5, 32. For 19, for 20 this will be 2 to the 20, which is close to a million. For 30 it is close to a billion. For 40 it is a trillion. It is a huge number. Okay. So, nobody can draw that. So, that's the way. How would you know the number of rows, the number of possible combinations of values? The way to see it, again we will see this thing, every new proposition, every next proposition doubles the number of rows in the truth table. So, the 1 has 2, 2 had 4, 3 had 8, 4 would have 16, every next proposition doubles the length of the truth table. Okay. There are more errors, you are going to make many errors. If I give you 4 possibilities, you will forget one, you will repeat one, you will whatever, a lot of mistakes are made, right. And it just makes it impossible to work with anything double digit number of bits or double digit number of atomic propositions. Just nobody can draw it, right. 2 to the 10 is already 1024, right. So, nobody can just draw it, you just do not have too much paper. So, we need another systematic way to establish the equivalence of 2 propositions. Okay. So, to prove 2 compound proposition, how do we do? How do we translate in a language statement, in English language statement into some other statement, equivalent statement? Translate or rephrase an English statement to another statement. The way to do it is, you start with the translation, with the original statement. You start with the original statement and you rephrase it such that it becomes more easy, it becomes closer to your target statement, right. Then you rephrase it equivalently, maintaining this equivalence. That is how we will, if you have an algebraic expression, how do we prove it is equivalent to some other expression. So, for example, if I have, just write bigger, I want to prove that this is equal to right. So, this is our general algebraic expression, this is what is called the Boolean algebra expression, right. How would I prove that this is equal to this? You must have seen in kindergarten this equivalence of logical expression, right. Simplify this logical expression. I would say, okay, this is equal to 3x plus 2x plus 7 minus 5. Then I will also write, because the first expression is because x squared divided by x is equal to x. So, I just replaced this x squared divided by x with x, right. Make sense? Then I would say it is equal to 3x plus 5x, 2x equals 5x plus 7 minus 5, and because 3x plus 2x is equal to 5x, right. This is the definition of addition, right. And then I would say, because 7 minus 5 is equal to 2, that is why finally I will get here that 5x plus 2, right, which is equal to what my desired value, right. This is equal to what was written, what was claimed to be equal expression for this, right. So, that is why I am done. Does that make sense? So, we want to do this type of way. This is the laws of Boolean algebra. There also we use this multiplication, division, this arithmetic, and then some operations or addition, multiplication operations. Do you remember any laws that governs this, that simplifies the addition, multiplication, subtraction of division of numbers? Associative law, commutative law. It's commutative law. You can add a number. 2 plus 3 is equal to 3 plus 2. Order in the addition does not matter. Add the summed. Associative law, multiple operations. Distributive law. What is the distributive law? Sorry. What is the distributive law? Say it, just say it loudly. Why do you say one word and then you stay silent? Oh, say it, don't worry. Let her say it. Say it. Let her say the same as what you want to say. You first say it, then she will repeat. Okay. Okay. So, we will come to the distribution thing, right. So, these are called laws. This is called laws, right. This is a law or something. It is a distributive law, associative law. So, we are going to do exactly the same thing there, and with examples hopefully it will clear. And I want to mention one specific thing about distributive law, because that is a distinction of Boolean algebra. So, the first is called identity laws, and earlier I asked you to wait for the questions when initially you asked question about tautology and contradiction, same proposition. So, that will come here. If you take any proposition P and you end it with the constant value constant value or true, what do you get? P and true is what? P, right. What does it mean when I say P and T is P? Can you please say that? Just the definition of equivalence. P and T is logically equivalent to P. What does it mean? What does logical equivalence of two propositions mean? Is this a proposition on the right hand side here? Is this the left hand side? P and T is also a proposition. I am saying these two propositions are equal. What does it mean? If and only if between the two will be a tautology. Yes, even simpler, that is a correct statement, but any other simpler version of this statement? They both have the same truth values. Okay? The left hand side P and T, the right hand side P have the same truth value. The right hand side truth value is P. So, it is saying the output is going to be equal to P, right. In other words, if P is true, P and T is going to be true. If P is false, P and T is going to be false, right. What is P and T when P is true? P and true when P is true? It is true and true, which is true, right. What is P and true when P is false? Because it is false and true, right. So, this is called the identity laws of addition. What is P or F? It is equal to P, right, because if P is true, then it will become true or false. that means it will be true. If P is false, then it will become false or false, which is false, right. So, the output is going to be equal to P, right, irrespective of the value of, so it is going to be depends on the value of P. Okay. Now, please remember one thing, in Boolean algebra or this logical algebra, it is called propositional calculus also. In this OR is called disjunction. It behaves more or less like addition. It is the binary version of addition, adding two numbers, right. The numbers in number theory when we do addition, and behaves more like multiplication, right. Those are two fundamental operations there. Now, there is nothing called like, this is a different algebra, that is a different algebra, but because we are so used to that, I have to say this thing. In numbers, when I multiply a number with 1, what do we get? If x multiplied by 1 is what? X, that is the identity law of multiplication. If I add 0 to x, what do I get? X plus 0 is what? X, right. That is the identity law of it. That is why 0 is called the, what is 0 called? The additive identity. What is 1 called? It's multiplicative identity, right. That is exactly what this true and false behave like. That is the 0 and 1 for this thing. In fact, here there is nothing more. There is 0, 1 and then a lot of other stuff built upon that, right, a lot of other bigger integers. And the dominations law, P or true is going to be true, irrespective of the value of P. If you OR something with true, if you OR P with true, you will get true, right, and you can try it. Let us put P equals true, we will get true or true, output is true. If you get P equal false and false or true, the output still is true, right. So, this is called the dominations law, the truth here dominates, right, and P and false is false, irrespective of the value of P. If you AND P with F, you will get F, right, the F will dominate over the value of P. Try it, P, plug in P equals true, you will get false, plug in P equals false, you will get false when you AND it with false. Is it clear? Yes. Similarly, there is idempotent laws, P or P is always equal to P and P and P is also equal to P, right. Nothing there to just try for what possibilities of P, values of P, true and false, you will see that. There is a double negation law, the not negation of P is equal to P, right. If P is true, again do that type of analysis in your head, it should be very quick. If P is true, what is not P? P is true, not P is what? What is not of false? True. P was true and not P is also true. If P is false, what is not of P? What is not of true? False. So, P is false, not P is also false. So, they are equal, right, the double negation law and the negation law. P or not P is, what is P or not P? That is a tautology. Remember, P or not P is a tautology, it is always true. So, this is a very shorthand way of saying P or not P is a tautology, irrespective of the value of P, or for both possible values of P, P or not P is going to be true. Okay? And P and not P is a contradiction. P and not P is equal to F, whatever the value of P is. Does it make sense? Anyone, any question, any issue here? No? Any objection? No? Okay. De Morgan's law, we saw that one version of it. The negation of P or Q is equal to just not P and not Q, right. This is very important. We will see a lot of this stuff in when we do predicate calculus, predicate algebra tomorrow. P not of P or Q is equal to not P and not Q, and not of P and Q is equal to not P or not Q, right. So, the sign changes, the negation goes inside and disjunction is changed to conjunction and conjunction is changed to disjunction and switches to. That makes sense? We saw one of these equivalences in the truth table, through the truth table. These are also equivalences just like claims. I showed you this one, I showed you this one there, right. For all others also, some we just described it in the previous slide also. The negation also, we double negation, we saw that. You should go home and make a truth table and verify via the truth table that these equivalents actually hold, right. They are actually valid equivalences, right. Here are some more. The commutative law of, just like we have commutative law for numbers and addition multiplication, P or Q is the same as Q or P, right. Order of operation, order of these P or Q is they commute, right. They can just, you can swap them, P and Q, and try to make the truth table of them. Try to make the truth table of P and Q and also Q and P. You will see they are exactly equal. When we take the truth table of P and Q, we say both are true or one of them is false, right. Not if P is false and Q is true or something like that. So, P and Q is the same as Q and P, P or Q is the same as Q or P, right. It is not the same for P implies Q. P implies Q is not the same as Q implies P. P implies Q is not the same as Q implies P. What does it mean? What is Q implies P? For P implies Q, what is Q implies P? It is the inverse, right. The inverse is not the same as an implication, that you cannot commute, right. They do not commute. P implies Q is not the same as Q implies P. Q implies P is the converse, Q implies P is called inverse. It is called converse, sorry, it is called converse, whatever. This converse and inverse are exactly the same to each other. Converse is the contrapositive of the inverse and vice versa, right. So, converse is not the same. So, if x is a general, x is an idiot is not equivalent to if x is an idiot, x is a general, right. That is how you should remember it. Then the associative law, P or Q or R, here if they have the same operation, the order of those addition or multiplication or and or is not going to make a difference. P and Q or and R is the same as P and R, P and Q and P and R, right, whatever I said, right. So, these parentheses, if the same operation you can. Then is this finally the distributive law. P or Q and R is equal to P and Q or P and R, right. So, this is okay, this is or P or Q and this and then P or R, and P and Q or R is P and Q or P and R, right. So, here we say or distributes over ands and distributes over or, right. So, disjunction distributes over addition over conjunction, and conjunction distributes over addition over disjunction. This is not true for numbers. For addition and multiplication, this is not true, right. Addition does not distribute over multiplication. What is this? 7 times 2 plus 4. Quickly, what is 7 times 2 plus 4? What is 2 plus 4? It is two big numbers, right. So, let us make it small. I won't be able to do this arithmetic. What is 2 plus 4? 6. What is 6 times 3? 18. Now, what is 3 times 2 plus 3 times 4? 3 times 2 is 6 and 3 times 4 is 12 plus 18. 12 plus 6 is 18. So, they both are equal, right. So, we know that multiplication distributes over addition, right. But if you do it the other way around, if addition does not distribute over multiplication, what is 3 plus 2 times 4? What is 3 plus 2 times 4? 2 times 4 is 8 and 8 plus 3 is 11. And what is 3 plus 2 times 3 plus 4? 3 plus 4 is 7, 35. see they are not equal. Listen, addition does not distribute over multiplication, multiplication distributes over addition. In Boolean algebra, I told you OR is more like addition, AND is more like multiplication, but that's fundamental difference here. Here OR distributes over AND also AND distributes over OR. Okay. So, these are the distributive law. One of them we saw, we proved it using truth table. For the other also you make truth table and say make sure you convince yourself that they are equivalent, right. So, now let us use these, please. Yes, please say it again. What if the same proposition has a AND and a OR? What do you mean the same? Is it P or P? And Q. Okay. So, instead of 3 proposition, what if there are 2 propositions? That is what you are saying? P and Q or R, then it will become this thing. Okay. Will the order matter? Got it. Got it. I think I got it. Right now, when I stated associative law, I explicitly said it. Okay, if there is the same operation, this is what you do, right? You can do it in any order, right? If they are not the same operation, first you will have to do with the brackets, and so let me. Can you write here? Can I come to this in a minute? Okay, so we'll come to. Hopefully, we'll get some examples. We'll make it clear, because I think I got your answer, your question. So you are saying P and Q or R. P and Q or R. No, okay. So yes, you are right. This will not make a difference, but we will come to that. Okay. Let me just go through a little bit more things for on the slides, and then we'll come to hopefully your questions. S and Q or not P, or P implies Q or not Q implies not P. How many propositions are here? How many atomic propositions are here? Right? 3. So, the truth table is going to be very long, right. So, let us do it through the laws, right. So, let us simplify, let us rephrase it and see if it is actually equal to true value, right. So, what can we do first? This is what we are given, this is the original thing. We can apply, like for example, here we can apply the implication law, and then it will become something like not P or P, and then we can apply, here we can apply the distributive law of OR over AND. Here we can do some other stuff. So, let us the first thing we are using is implication law. Implication law says A implies B is the same as not A or B, right. So, here P implies P would mean not P or P, right. You either did not solve the Goldbach conjecture or you got an A. Okay. So, not P or P, what is not P or P? Not P or P is a tautology, right. P or not P is a tautology. So, we write that it is the negation law, not P or P is true, is always true. So, we will write it as true, right. Then we can apply true or this thing, this is the domination law, true or anything is actually going to be true irrespective of the value of this whole thing S Q and not P, right. Yes, because true or thing, this is a true or something not Q and P. What will be true or not Q and P? Again the domination law, true or anything is going to be true, right. So, by the domination law, by these successive applications of laws, different laws, we got that our original proposition is logically equivalent to true, and that is the definition of a tautology. Irrespective of the value of P, Q, R, S, whatever, the value is going to be is equal to true. Is this clear? Let us do one more example that you are going to do later. Are these two things equivalent, right? Now, those of you see it's a very complicated thing on the right hand side, right. So, if you have a if condition in your program, which says that if P, Q and P or not the negation of Q implies P, Q implies P, you can write in implication for by applying the implication law, you can easily write it in C++, right. But instead you just write if Q is true, then do execute this code, and that's much simpler. That's how, why would you like to use equivalences, right. So, what can we do here? We start with the right hand side and we show that this is actually equal to Q. What can we apply? Generally speaking, the first thing you should get rid of implication. They are derived things, just simplify them, make the game all if and or and not, right. So, get rid of implication, apply the implication law, what will you get? Not Q or P, right, instead of Q implies P, and the rest everything will remain the same. Then we can apply perhaps the De Morgan's law, the negation of two things, of the negation of a compound proposition, apply the De Morgan's law. We will get not Q, or will become and will become not P. Okay. So, not Q, what is not Q? Double negation law, it is equal to Q, right. So, Q and not P and Q and P. What is this? Q and not P and Q and P, or Q and P. It is a distributive law, okay, of addition over of and over or. This is actually Q and P or not P. Can you see this? What is P or not P? Q or not P is a tautology, right. P or not P is by the negation law, P or not P is always true. What is Q and true? Q and true is by the idempotent law, it is not the domination law, it is the idempotent law, it is equal to Q, right. So, we got that the left hand side is indeed equal to the right hand side by applying these laws in these orders, right, by successively replacing the original statement on the left hand side with equivalent statements, and we got this. You see this series of equalities, it gives us that this thing, the last line is equal to the first line. Okay, let us do one more thing, because I want to go to that this perhaps would be one of the last examples that we do. P implies R or Q implies R is equal to P and Q implies R, right. This is what we are given originally on the left hand side. What shall we do? Get rid of implication, most probably that is what we should do. P implies Q is equal to not P or Q. Then get rid of the other implication, Q implies R is equal to not Q or R, right. Then what is common in these two? Both is R, but both all the operations are OR. So, this will be associative law. This is actually not P or not Q or R, right. It is just the same operations. You can do first these two, then those two, or first the middle two and then add the last one, right. The order of these operations, because the same operation. Then what we can do, R or R is equal to R, that is idempotent law, and then apply the implication law, not A or B is equal to A implies B, right. So, this is equal to, so we first applied by De Morgan's law, not P or not Q is not of P and Q or R. Now, apply the implication law, is equally equal to P implies Q, P and Q implies R, right, and that is equal to, okay, 2 steps there. Make sense? Yes. So, yes, these two are equal by applying these laws in this order and replacing each statement with the equivalent equal statement, right. So, we established logical laws using truth table. It was very cumbersome method.
Sir, how did that or become an and?
Which or? This or?
How did that?
This or? That is a De Morgan's law. The De Morgan's law. De Morgan's law says negation of and of two things is this the or of negations. And negation of or of two things is and of the negations, the individual negation. Please stay here. I have a question, standing question here. G. Idempotent laws is P Where is it?
R or
R or R is equal to R. It's either true or true if R is true, or false or false, right? What was the question, please? Somebody asked some very good question and I want to talk about that. Can you please dictate to me what was your question? Who asked the question? Yes, please. P and Q, any brackets, anything? No? And what? Any order, that's not going to be important. If you put in bracket, then you should do this first, even though it's not going to make a difference. No, wait, what? If you put in bracket, then you will have to apply the distributive law. Now, this OR is applied to both of them, right? But if you don't put the bracket, then you can do either this one first or this one first. These two first. That was your question?